Welcome to Backyard Philosophy, a podcast where a couple friends grab some cold ones, sit around the fire, and talk about science, philosophy, and history. Crack one open, sit back, and get a good laugh as we discuss everything from automation to why the meaning of life is 42. Since the beginning of the human race, we have looked to the stars and pondered, what is this world, this universe? What makes up the things we hold in our hands, and why do they exist? And occasionally, just occasionally, you get to figure out how the universe works by smashing things together. Today we're going to be talking about the Hadron Colliders and how they work. But before I get into the world of physics and engineering, Nick, how are you and what are you drinking?
I'm not drinking enough for this episode, I'm guessing. I got some Gatorade here because I got stuff to do tomorrow. What about you?
I'm drinking some 9 branded bourbon. Quite smooth. Wish I had a little bit more bite though. But, Nick, we're in my world now. I can shake it loose. Engineering and physics at its finest. Some preface before getting into how accelerators work. There are many accelerators in the world, almost 30,000 of them. Some small in university basements and some large, stretching between 2 countries. All around the world, scientists are working towards discovering what makes up the universe. Many of these accelerators are smashing particles together to see how hadrons work or new hadrons they can discover, hence the name Hadron Collider. A hadron is a class of subatomic particles, and hadrons last for an extremely short time and they rapidly decay and are absorbed. And the reason why we want to study them is for a large range of reasons. If we find a new subatomic particle, it may help us find a standard model, might prove or disprove certain theories, and teach us more about matter itself. And in case y'all are not familiar, the standard model is the theory of what makes the universe what it is. Now that we know what we're aiming for, how do we look for it? That is where the Hadron Colliders come in. It is a way to precisely, in a controlled environment, smash particles together and see what happens. But how does a Hadron Collider work? Well, it starts with a series of sectors. The Large Hadron Collider, which I assume many of you have heard of, is made up of 8 sectors. Each sector is an arc connected on each end by a section called an insertion. These sectors range in size. For the Large Hadron Collider, the circumference of the sectors total in 27 kilometers. That's 16.8 miles. Each sector is made up of an assortment of things. Sensors, magnets, cooling systems, electrical field generators, all important pieces to play in the orchestra of collision. Let us start with the cooling system. The cooling system is to help with the magnets. They use magnets to propel the particles along with electrical fields. Also, the Hadron Collider uses about 9,600 magnets. And for those who don't know, when you change the temperature of material, it changes its properties. So, if, for example, you were to take a magnet and supercool it, it would make the magnet have certain super properties. So liquid hydrogen and helium are pumped to the magnets. And for the Large Hadron Collider, they cool the magnets down to about 1.9 degrees Kelvin, which is about negative 456 degrees Fahrenheit. They use about 10,000 tons of liquid nitrogen and 60 tons of liquid helium to bring down everything to the right temperature. Next, inside the Hadron Collider, you have to pull a vacuum. No, Nick, you can't use a vacuum cleaner.
Just turn it from suck to blow.
Oh, Spaceballs, haven't seen that movie in forever. But you are trying to pull a vacuum as though you're in the depths of space. And pulling a vacuum serves a few purposes. The first is removing contaminants. You can't have any dust, any gas, any particles. You gotta be even careful with light entering in. Because if there are any particles besides the particles you put in, and you're sending particles that you want to collide with specific particles, one atom of a misplaced gas particle or a speck of dust could ruin the entire experiment. Hell, like I said, with light, can entirely affect the experiment. So engineers and scientists must get a near perfect vacuum inside the collider. Well, now you have the conditions, cold, lightless, in a vacuum. What about the particles themselves? Scientists use a controlled burst of particles, firing them in both directions so they will cross each other. These bursts are called bunches. They're made of about 100 billion protons. The protons and the particles they tend to use in such experiments are hydrogen ions, or hydrogen-based. So you shot a beam of particles going one way, and then another set going the other way. From there, you use magnets, which are now supercooled, and electrical generated field, which is just sending electricity to help push the particles fast. And I do mean fast, near the speed of light itself. And as the speed gets picked up and going faster and faster, these beams are moving so fast that in about a second, they'll make they're moving so fast at top speed, these beams make 11,245 trips around the 16.8 miles of track every second. Once you have your bunches up to speed, traveling around and around and around, you start crashing them into each other. You not crash them all at once, you take passes at them like you're skimming off the top, crashing the particles section by section. These high-speed crashes cause the particles to break down into smaller pieces, hadrons, and give us insight to what make particles particles. Each pass, more data, and more crashes. As the experiment continues, you can imagine that a bunch of particles in a far less than previous state, since it's been crashed so many times, may have dislodged some of the particles from the herd. In order to get the particles back in order, the scientists use a quadrupole magnets. And how this process works, it's not exactly like this, but I think it's a good analogy. Play-Doh. If you've ever played with a clump of Play-Doh and you want to get it organized in a straight line, you put it through a mold. You squeeze it through, drawing the Play-Doh out like metalworkers draw a wire through a gauge block. The mold for the Play-Doh, making the Play-Doh more organized, thinner, pushing them exactly how you want them. It's kind of what the quadrupole magnets do. They condense the beam, kind of reshape the beam as a mold, get them condensed and organized. This process is repeated again and again and again until the experiment is complete and all the particles have been smashed together. During this entire colliding process, thousands of different types of sensors have been recording and observing the entire experiment the entire time. In the Large Hadron Collider, there are nearly 150 million sensors laid out throughout the collider, ranging from devices like a calorimeter, a device that measures the energy of particles by absorbing them. Then, not to mention your cameras, your temperature sensors, your muon spectrometers. A muon is a subatomic particle which is negatively charged and 200 times heavier than an electron, and it can travel through a calorimeter. So it needs its own special device to monitor and record the data. But now you have all this data. You need to process it. The amount of data collected by a Large Hadron Collider is 700 megabytes per second. And it collects about 15 petabytes. That's 15 million gigabytes per year, for those not familiar with the conversion, which is a lot of data. That's just so much data.
How much does it cost to run one of these?
I know that they can't run it during certain seasons because the air conditioning and heating is too expensive.
Makes sense.
That's for the Large Hadron Collider. Again, they come in all shapes and sizes. Depending on your university or your business, you might be able to run it anytime you want, depending also on the size. But with all this information, scientists have to break it down in chunks, which they call tiers, or else they'll never get through it. And through this information processing, they can get an accurate representation of what just happened. For example, I imagine most have seen, or at least can imagine, particles hitting each other. Parts flying every which way, usually different colors, the same way as a car crash. And the computer, coming up with the image to represent the trajectory of the flying off parts, can tell a lot what just happened. So if you break off a piece and it curves and it flies away from the collision that you just crashed with the particles, you can tell the charge of that subatomic particle that you just made by the radius of the curve. So you have to measure everything as you're doing this. And once you have all that data processed, you can see if the experiment was a success or if it's back to the drawing board. Some interesting facts I thought you might like, Nick, before we conclude on Hadron Collider's work. The Large Hadron Collider, which is where most of my research was on, is buried 100 meters below. That's about 330 feet below Earth, and crosses the border between Switzerland and France. And to run it, it takes 800,000 megawatts to run. And the first time the Large Hadron Collider collided two beams was November 23rd, 2009. And to date, it has helped discover...
I feel like I remember that because that was... Everyone thought the world was going to end when they did that.
Oh, let's be honest. Everyone thinks the world's always going to end.
Fair point.
And to date, the Hadron Colliders have discovered either 59 or 60. Not quite sure. They announced a new discovery this August of 2021. But as March of 2021, they were at not 50 hadrons, might be already at 60. But that's pretty much how a Hadron Collider works. You shoot some ions or particles in a very cold, controlled environment, use magnets and electrical fields to get the things spinning super fast, and then you crash them together. And Nick, hopefully I made a good example of how it works, at least a good 101 crash course for Hadron Colliders.
I knew it was coming. No, I definitely know. I always knew they were there, and they were impressive, and and we learned a lot from them, but I never knew more than that.
Well, like I said, there's about 30,000 throughout the world, so there's probably one within 100 miles of you, Nick.
That I doubt.
Well, there's got to be some universities in your state, right?
Yeah, more just of how far I am from things. But yeah, there's probably some here. Or not. The people of Oregon probably protested their way.
Well, before we get into the politics, the science behind it, it's simple yet complex, and I love it. And I hope I made it a little bit easier for everyone to understand what a Hadron Collider is. Thank you all for listening.
Thanks for listening to the Backyard Philosophy Podcast. We rarely finish a podcast without missing a point we wanted to bring up, so let us know what we forgot. And if you have a topic you want us to talk about, let us know at Backyard Philosophy on